The first keynote speaker is Professor Doo-Yeol Yoo. He's from South Korea. So Professor Yoo is a professor in the Department of Architecture and Architectural Engineering at Yonsei University, top-ranked university in South Korea, and an affiliate professor in the Department of Civil Engineering at the University of British Columbia, Vancouver, Canada. With over a decade of expertise in ultra-high performance fiber reinforced concrete, cement-free binders and CO2 capturing concrete, and multifunctional cementitious composites, he is internationally recognized as a leading researcher in these fields. He has received several international awards and is recognized among the top 2% of scientists globally in the field of building and construction. So please join me in welcoming Professor Yoo.
Good morning, everyone. I'd like to express my sincere gratitude to Professor Tuan, who is the DBI network convener, and to Professor Ali for inviting me to serve as a keynote speaker at the DBI workshop hosted by Flinders University in Australia. I am delighted to share knowledge and ideas with my colleagues as we work together toward a sustainable future. Today, I will give a talk about toward a sustainable future, eco-friendly, high-ductility slag composites for construction materials. As of 2023, Korea ranked 13th globally in greenhouse gas emissions with approximately 12 tons of CO2 emitted per capita. As shown in this figure, Korea is heavily dependent on fossil fuels as an energy source, accounting for about 40% of its total energy sources. This value is considerably higher than other developed countries such as Japan, Germany, and United States. For this reason, Korea's greenhouse gas emissions have continuously increased since 1990, and in 2018, the greenhouse gas emission was highest as 727.6 million tons, and it slightly declined to 691.6 million tons in 2024. The Korean government has set a target of reducing greenhouse gas emissions by 24.4% by 2030, relative to 2017 level, with a reduction of 10 million tons expected from the building sector. In the building sector, approximately 69% of greenhouse gas emissions occur during operation, while about 28% arise from materials production. Therefore, from the perspective of construction materials, a reduction of 2.8 million tons of greenhouse gas emissions is required up to 2030. And one of the major greenhouse gases is the carbon dioxide, which is significantly produced during cement production. The global cement market size in 2023 was $410 billion, and it is expected to increase up to $650 billion in 2033. The increase of market size is good for our industry. However, in terms of environmental sustainability, as a scientist, we need to reduce the cement consumption. As we already know, 1 ton of cement production produces approximately 0.9 tons of carbon dioxide equivalent, which is mainly caused by fossil fuel and calcination in the clinker kiln system. In addition, approximately 13.5 million tons of waste tires are generated each year. Among them, 72% of waste tires are used as energy for producing 932 kilograms of CO2 equivalent per unit, while only small amount of waste tires are recycled into other products. Therefore, to achieve environmental sustainability in construction materials, it is necessary to develop cement-free concrete incorporating such waste material. And to reduce the cement consumption, the concept of alkali activated concrete was first introduced in the early 20th century, long time ago. In this approach, precursors are typically activated using sodium or potassium-based activators. However, Such activators generate significant heat in the solution, requiring the solution to be prepared at least 1 day or a few hours before mixing. In addition, because setting occurs extremely rapidly, sometimes within just a few tens of minutes, practical applications in large-scale structural elements remains highly challenging. The sodium ions also tend to leach continuously from the relatively weak Nash gel, which not only reduces the long-term strength, but also leads to efflorescence, blah, blah. As a solution to these limitations, calcium-based alkali activator was recently proposed. Since the calcium-based activator is similar to the early hydration product of ordinary cement, it can effectively prevent rapid setting. In addition, this can promote the formation of cash gel, which exhibits stronger bonding than the Nash gel, thereby mitigating the long-term strength reduction and suppressing efflorescence. Such new activators can be obtained as byproduct from seawater-based industrial processes. For instance, wastewater, rich in magnesium and calcium ions, generated from refined salt production, can be utilized. In the first step, the pH of the wastewater is adjusted using sodium hydroxide. As the pH increases, the magnesium and calcium ions in the wastewater react with hydroxide ions, precipitating as calcium hydroxide and magnesium hydroxide. As shown here, the calcium hydroxide typically begins to precipitate at pH levels above 11. In addition, the XRD and TG analysis confirm that the resulting byproduct is the crystalline calcium hydroxide. So we adopted this calcium hydroxide as a new activator for fabricating the cementless strain-hardening slag compound. And this is the chemical and geometrical properties of raw materials and mixed proportions. The blast furnace slag was used as the main binder instead of cement, and it is activated by the powder type calcium hydroxide. The XRD patterns of the slag and silica film show that they have high amorphous bases with small quantities of crystalline minerals. And also the size of crumb lava was quite similar to that of silica sand. And the silica sand was progressively replaced with the crumb lava up to 80% with an interval of 20%. And the amount of calcium hydroxide was determined to be 10% by weight of the slag based on preliminary test for pH and chemical concentrations in the pore solution and thermogravimetric analysis. And this is the mixing process and the pre-treatment of the crumb lava. The waste crumb lava contains stearate, which originates from the zinc-based fillers used in the tire production. Due to its hydrophobic nature, zinc stearate weakens the interfacial bonding with the matrix. To address this issue, the waste crumb lava was pre-treated with a 10% sodium hydroxide solution to remove the zinc stearate layer from its surface. The detailed process is shown here. And according to the EDX result, the zinc was completely eliminated, while a small amount of hydrophilic sodium hydroxide was found to remain on the surface. And the pH in the pore solution, as you can see here, increased by increasing the amount of calcium hydroxide. And most importantly, from 7.5 to 10%, there was the largest increase of the pH value. In addition, the silicon concentrations in the pore solution start to decrease obviously from the 7.5% of calcium hydroxide, meaning the lower calcium and silicon ratio in the CSH gels, which is effective for the strength enhancement. And based on the derivative gravimetric result, 10% and 12.5% of calcium hydroxide produce the highest amount of CSH gels. So even though it is difficult to conclude that 10% calcium hydroxide is the absolute optimum dosage, this level is close to the optimum in terms of the hydration reactions. Therefore, 10% calcium hydroxide was adopted in this study. And this is the compressive strength of the calcium hydroxide activated slag compound without polyethylene fibers. The highest compressive strength was achieved in the plain sample here with 2 mole fractions of the polyethylene fibers, indicating the well dispersion of the fibers in the matrix. And by replacing the silica sand to the crumb blubber, the compressive strength showed a decreasing trend caused by inherently lower strength of the crumb blubber than the silica sand. So in the case of 80% replacement, the lowest compressive strength of 44.2 megapascal was obtained, which is approximately 70% lower than the plain sample. And following the Japan Society of Civil Engineers recommendations, we conducted the direct tensile test. Initially, 5 dopant samples were fabricated and tested for all tested variables. However, by excluding some specimens that developed cracks at the neck, 3 to 5 specimens were used for obtaining the average data. The tensile stress and strain curves were then averaged by the interval-based linear interpolation. And this is the average tensile stress and strain curves with various dosages of crumb blubber. The plain sample grade 1 here exhibited the general strain hardening behavior. By replacing the silica sand up to 40%, even though the tensile performance was improved, there was no change in the shape of the tensile stress and strain curve. However, when the replacing ratio was 50% or higher, the initial post-cracking stiffness was obviously reduced, and there was a re-increase of the tensile stress, indicating the second strain hardening behavior. And this is caused by the decreased matrix cracking strength by crumb blubber acting as flows and synergistic crack bridging effect of the crumb blubber and polyethylene fibers, as you can see here. And as you can see here, the crumb blubber effectively bridges the cracks, micro cracks. And this is the schematic description of flow size tailoring in the strain hardening cemented composites such as ECC, engineered cementitious composite. And to achieve a slow strain hardening behavior with fully saturated micro cracks, the Griffiths type crack with substance need to be changed to the steady state flat crack with limited crack openings. For this, artificial flows having the size greater than the critical flow size need to be provided, which is crumb blubber in this study. And this is the typical tensile behavior of CR60 specimen. And after initial cracking here in the matrix, a general slow strain hardening behavior was observed up to the strain of about 5.5%. In this reason, multiple microcracks could be fully saturated in the flow dense zone with enough crumb blubber. However, after this point, the tensile stress starts to re-increase with the formation of additional cracks in this zone with only few or insufficient amount of crumb blubber. Once it reaches to the bridging strength of the polyethylene fibers and the crumb blubber, the tensile softening behavior with crack localization was observed. Therefore, this second strain hardening behavior is caused by the insufficient dispersion of the crumb blubber. And this is the summarized tensile parameters. As you can see, the crumb blubber dosages of 60% was the optimum, providing the best tensile performance with the strain energy density of about 453 kilojoule per cubic meter, which is approximately 1.5 times higher than that of the plain sample. And this is the crack parameter analysis. The plain and CL20 sample show the fewest microcracks and the widest crack openings over 300 micrometers at the peak strength. However, by incorporating the crumb blubber more than 50% here, the cracking behavior was significantly improved with the smaller crack width and higher number of microcracks. The CR60 sample showed the best cracking performance with the smallest crack width, and it successfully maintained the crack width below 180 micrometer, which is the self-healing threshold up to very high tensile strain of 7.3%. And this is the typical microcrack pattern comparisons between the plain and CR60 samples. As compared to the plain sample, this is the plain sample, by incorporating the crumb rubber, the maximum crack width was more effectively controlled, especially in the strain hardening job. So for the case of the plain sample, the maximum crack width continuously increased in the strain hardening job. But for the case of the CR60 sample, the increase of the maximum crack width was more effectively prevented, especially in the strain hardening. In addition, it was obvious that the CR60 sample produced fully saturated and much more microcracks at the peak point as compared to the plain sample. This verifies the benefits of using crumb rubber in terms of the decreased matrix crack tip toughness and the increased crack bridging effect. And this is the comparative normalized tensile behaviors of strain hardening slag composite that was developed in this study, and the commercial steel reinforcing bars, steel rebars. The CR60 sample here showed the highest strain capacity among the strain hardening slag composite, surpassing grade 500 rebar and reaching about 60% of grade 400 steel rebar here, confirming its exceptional tensile ductility. However, to fully eliminate the conventional steel rebars from structures in the future, that is actually my goal, in terms of reducing construction costs and mitigating CO2 emissions, the strain capacity need to be further increased. And to verify the sustainability of CR60 mixture developed in this study, the equivalent to CO2 emission, which is greenhouse gas emission, and the embodied energy are compared to those of 4 different types of HPF processes, such as ECC, and high strength and high ductility concrete, and ultra high performance concrete, and high strength ECC. Obviously, the CR60 mixture showed the lowest CO2 emissions of 346 kilogram per cubic meter, which is 67% lower than UHPFRC and 62% lower than high strength and high ductility concrete, having similar to or even lower energy absorption capacity. The embodied energy of CR60 mixture was also 32% lower than UHPFRC and 26% lower than high strength and high ductility concrete. Therefore, it can be concluded that the developed composite achieved superior environmental performance given similar to or even better tensile behavior as compared to other types of HPF processes. And this is the concluding remarks. Replacing silica sand to the crumb rubber reduces the compressive strength of strain hardening slag composite. The lowest compressive strength of 44.2 megapascal was observed in the CR80 specimen, representing a 70% reduction as compared to the control sample. And the tensile performance is significantly improved with the crumb rubber, and the crumb rubber, the CR60 specimen, shows the best result with a tensile strength of 8.3 megapascal, a strain capacity of 8.2%, and strain energy density of the 453 kilojoule per cubic meter, which is 1.5 times greater than the control sample. And the CR60 mixture provides the excellent crack control, forming about 70 microcracks, fully saturated in the gauge length, and maintaining the maximum crack width below 180 micrometer up to the strain of 7.3%, which ensures the enhanced durability, especially throughout the self-healing capacity. And based on the life cycle assessment, CR60 mixture developed in this study is the most eco-friendly mixture compared to other types of HPF processes, with the lowest equivalent CO2 emissions and embodied energy, which are 62% and 26% reductions compared to high strength and high ductility concrete. Okay, this is the end of my presentation, and thank you for your attention, and please feel free to ask if you have any questions. Thank you.